This is Mr. Anderson for Kellogg Community College, and thank you for watching Part 4 of Chapter 3, Section 5, which is the sum and difference formulas. And we're going to take a look at some inverse functions and the sum and differences of their angles, and we can kind of show you some cool tricks with that. And one of these problems actually starts out, actually a little easier than most of these because of the inverse cosine of 1. Just to show you this, what we're going to do is figure out what these two pieces are here and then use the sum and difference formulas to kind of help us out there. So the inverse sine of square root of 3 over 2 happens at pi over 3. And I notice I only looked at the first quadrant because for sine, an inverse sine, I only look at the first and the fourth quadrant for these for these values, so I'm not actually looking at the second or third quadrant for inverse sine. Whereas cosine, I would look at the first and second quadrant, and the inverse cosine at 1 is actually 0. So this first problem actually gets done pretty quickly because now we just have to look at the sine at pi over 3, which is square root of 3 over 2. Where things get a little tough, though, is when we have to, now this is an example that shows you how to find things, but now we actually have problems that aren't findable on the unit circle, so we're going to have to take things in a little bit of a different approach here. For problem 14, and actually problem 15, I'm going to ask you, and 16, I'm going to draw triangles, and one of the nice ways to think about that is when you start problem 14, 15, and 16, you got to ask, the simple question is where am I? Because the inverse sine can happen in the first and fourth quadrants. The tangents also happen in first and fourth quadrants. So we ask ourselves these questions: where are we at? And this here is a negative 4/5, and since my choices are first and fourth, I definitely got to be in the fourth quadrant here. So what I'm going to do is consider this as my alpha and consider this as my beta. So my alpha triangle in the fourth quadrant right here, so here's my alpha, is going to be negative 4/5, and alpha, or sine, is opposite over adjacent, so here's my negative 4 and here's my 5, which makes sense since my y value is negative. And now I'm going to take a look at my tangent, which is positive. So you notice that my tangent's positive, so if I'm either in the first and fourth quadrant and the tangent's positive, then I've got to be in the first quadrant, because my tangent would be negative if I was in the fourth quadrant. So this is going to be opposite over adjacent. Here's my beta. Now we have to find these missing sides, and as I said in a previous video, if you see a 3 and a 4, the missing side is going to be a 5. Or in this case, missing side would be a 3. This is all because of a squared plus b squared equals c squared, or x squared plus y squared is equal to the hypotenuse squared on these right triangles in related to the unit circle. So you can see that 14 and 9 make 25, and all of this can be played out if you want to see that. And I can show you on separate videos where I've done that. But now what I'm going to do is I'm going to have my sine of alpha minus sine of beta. So this really is a sine of alpha minus beta problem, which I can then convert to the sine of alpha cosine of beta minus the cosine of alpha sine of beta. So now I actually go to my triangles and see where those interact. So the sine of alpha, which is going to be my negative 4/5, because that's opposite over adjacent, or opposite over hypotenuse, excuse me. Cosine of beta, so that's my adjacent and hypotenuse, so that is going to be 4/5 here, minus cosine of alpha, that's adjacent over hypotenuse, that's 3/5, and the sine of beta, which is my opposite over hypotenuse, which is 3/5 here. So what I have here is negative 16/25 minus 9/25, and so my answer to the problem is negative 25/25, or negative 1 is my answer for that problem. One of the other Pythagorean triples that should be pretty common is, I mean, because if you're wondering, well, what's a Pythagorean triple? Pythagorean triple is the 3, 4, 5. Another very common Pythagorean triple is this one here, which is going to be the 5, 12, 13. That's a common Pythagorean triple. So what this means is that here we have, another cosine of, here we have an alpha minus beta. And what we're going to do is set up an alpha triangle and a beta triangle. Now you'll notice that this tangent, inverse tangent, is positive. So if my choices are the first and fourth quadrant, I'm going to choose first quadrant. And my first quadrant is going to have tangent, which is opposite over adjacent. That is the definition of tangent, which means that my hypotenuse is 13. Because 144 and 25 make 169. Square root of 169 is 13 in this case. Now my sine is negative, so if I choose between the first and fourth quadrant, I'm choosing fourth quadrant, because the sine is negative in the fourth quadrant, not the first. So my opposite is going to be, since sine is opposite over hypotenuse, this is negative 3 over 5, and so this is a distance of 4. Another 3, 4, 5, 3, 4, 5, or 5, 12, 13 triangle. Alright, so now I get to play my formula here. So this is going to be the cosine of alpha, cosine of beta, plus sine of alpha, sine of beta. Now I'm going to go and take a look at what is my cosine of alpha. Here's my alpha angle right there. So alpha cosine 12 over 13, and cosine of beta, so here's my beta angle right there, and that's 4/5. Plus the sine of alpha, sine is 5/13, and the sine of beta, so here I'm sine of beta negative 3/5. So 12 times 4, we're going to do a little multiplication here, 48, and 13 times 5 is 65. Minus, since we have 5 times 3, which is 15, I change it to a minus. I could have put plus minus. 15 over 65. So 48 65ths minus 15 65ths is 33 65ths, which cannot be reduced. So for our final problem here on our worksheet, let's make some room for it here. Looks like we got another cosine problem. That's kind of nice. So cosine of alpha plus beta. Alpha plus beta. Okay, so the tangent is in positive 4/3. So since the tangent is positive 4/3, it looks like I'm in the first quadrant right there. And I'll put this in parentheses here. So here's my alpha. My tangent is 4/3. So that means I'm opposite over adjacent. This is going to be 5 because that is the Pythagorean triple there. 4 squared plus 3 squared is equal to 25. The square root of 25 is 5. The cosine is positive, and cosine when we do inverse cosines, we only look at quadrants 1 and 2. And since this is positive, we're going to look in the second quadrant, or sorry, first quadrant. If it was negative, I would look in the second quadrant, but it's going to be positive. So cosine of beta is 12/13, so this is my adjacent over hypotenuse. So my 12 looked like a 13, because I think I wrote a 13. And then my missing side here is 5. 13 squared minus 12 squared is going to be what's left here, which is 25. Square root of 25 is positive 5. All right, so the cosine of alpha plus beta is cosine alpha cosine beta minus sine of alpha sine of beta. All right, so what we'll do here is we'll plug in what we know, alpha beta alpha beta. So our cosine alpha, cosine is going to be my, let's see, adjacent over, sorry, cosine alpha, that is going to be my opposite, adjacent over hypotenuse, so 3/5. And my cosine of beta, better multiply these, cosine of beta is going to be my adjacent over hypotenuse, 12/13. Sine of alpha is going to be my opposite over hypotenuse, so 4/5. And sine of beta is going to be my 5/13. All right, and we got some multiplication to do again. So what we have here is 3 times 12, which is 36 over 5 times 13, 65ths, minus 5 times 4, or 4 times 5 is 20 over 5 times 13, 65ths. This simplifies to 16 over 65ths, which is the reduced form. And so that ends our problem there. Okay, well, thank you for watching.